Okay, so for this exam review, we're going to go kind of quickly just because a lot of you guys are already provided the worked out exam reviews, and we have a lot of questions to get through, so we want to make sure that we can get through everything and kind of show our thought process as we're going through it. So starting with section 1.1 functions, our main focus is just going to be looking at when does this function break. So here we're going to say, okay, finding the domain of each function using interval notation. We're going to say here, because we have x plus 2.9 in the denominator, in our numerator, say x cannot be negative 2.9. Based on this, x has to be greater than negative 6.4, greater than or equal to. So our domain is going to look like negative 6.4 included, up to negative 2.9, union negative 2.9 up to infinity. Now moving on to the next question, we're going to look at our denominators, or look at our numerators and see, okay, well, x minus 3 cannot be 0, and 5x plus 4 cannot be 0, which means that x cannot be 3 or negative 4 over 5. Everything else is okay. So we're just going to go ahead and say that our domain goes from negative infinity to negative 4 over 5, union from negative 4 over 5 up to 3, and then another union from 3 up to infinity. Perfect. Moving on, looking at our numerators, we know that x cannot be 0 and x minus 1 cannot be 0. So our domain is going to look like negative infinity to 0, union 0 to 1, union 1 up to infinity. On the next one, we know two things. First of all, 1 minus x cannot be 0, and 1 minus x must be greater than 0. So we know that x cannot be 1, and x is less than 1, which means that our domain is going to go from negative infinity up to 1, and that's it. Moving on to the next one, we know, again, two things. X plus 1 greater than or equal to 0, 2x minus 2 cannot be 0. So from this, we have x is greater than or equal to negative 1. Then here, we have x cannot be 1. So going ahead to our domain, we're going to start at negative 1, go up to 1, union 1 to infinity. Perfect. Then moving on to the last one, we know that x minus b greater than or equal to 0, and x minus a cannot be 0. So we know that x is greater than or equal to b, and x cannot be a. But, based on what we were given, because a is less than b, x can never be less than b, so it's not possible for x to be a. So we don't really have to, this can be ignored. We don't really have to pay attention to that because that's already excluded from this domain. So we know that it's going to go from b up to positive infinity. There we go. Moving on to section 1.2, we're looking at the average rate of change. So this is going to be based on, or the way that we're going to evaluate this is just we're going to look at y2 minus y1 over x2 minus x1. So here, it'll look like f of negative 5 minus f of 1 over negative 5 minus 1. That is going to give us a value. Go ahead and plugging it in. We'll get negative 30 over negative 6, or 5. The next two are going to be in the same way. So f of negative 3 minus f of 1 over negative 3 minus 1 will give us negative 40 over negative 4, or 10. And then from there, f, just onto the last one, f of negative 1 minus f of 1 over negative 1 minus 1. That's going to give us negative 30 over -2 this time, which has an average rate of change of 15. Okay, on to section 1.3. We're looking at the graph with this domain. Here, we're finding each of the following. If it doesn't exist, we're just going to put NA using interval notation. Okay, so it's increasing on the graph, as we can see. Up to here, it's increasing, and then between these two, it's increasing. So my notation is going to look like -infinity to 4 union with 9 to 12. And all of these are going to be unincluded because they're kind of like our endpoints. And then it would be decreasing in this range. So from 4 up to 9. Moving on to our local maximum, that is going to occur here. This value is technically higher, but we cannot have a local maximum at an endpoint. So our local maximum is going to be at x equals 4, y equals 36.5. Now on our local minimum, that value is here. So we're going to say at x equals 9, y equals -26. And then finally, our absolute maximum is going to occur here. So that will be at x equals 12, y equals 68.5. Absolute minimum, we can see that our function kind of keeps going down and down and down and down to the left. So this is not going to have an absolute minimum because it's never going to stop decreasing. Now for concavity, we are going to go ahead and look at when is our graph kind of shaped facing opening upward. So it's going to be concave up. We are going to be looking at kind of our local minimum is where that's going to be centered around. And we can see that in this area, it's concave up. So we're going to say that is from 6.5 up to 12. And then that means this area would have to be concave down, which is -infinity up to 6.5. If we notice, our cutoff point is here at 6.5. So that means our inflection point is going to be when x is equal to 6.5. Awesome. Now moving on to the next section, we're looking at the limit as x goes to infinity for each of the following. So if this first one, we're going to think about as x gets really large, here, what is the function going to do? So as x gets really, really big, this x plus 1 is going to get really, really big, which means that since we're dividing it, the whole thing is going to get really, really, really small. So y is going to approach 0. Moving on to the next one, it's not super clear from the get-go. So what I'm going to do is I'm going to multiply it by x squared over x squared, which will give us 5x squared minus x over 3x squared plus 2. If we notice, the power is the same on top and on bottom, which means that as x gets really big, y is going to become the ratio of those two values, or 5 over 3. On the next one, we see that the bottom has a higher power than on top, so we know that y will go to 0. And then on the last one, we know that the x's are to the same value, or are to the same power. They have the same degree. So y is going to become the ratio between the two of them. Awesome. Okay, now on to section 2.1. We're looking at getting new functions from old ones. We're given that f of g of x is 3 natural log of 2x minus 1, and g of f of x is natural log of 6x minus 2. So I'm noticing that we have this natural log in here. So because g is an inside function, I'm just going to say, let's just say that g is natural log of 2x, which means that here it's taking the place of x. So we're going to say, okay, well, f of x would have to be 3x minus 1 for this to be the case. Then going to the other composition here, we would see, okay, natural log of 2 times 3x minus 1. That does indeed give natural log of 6x minus 2. So we are all good there. Perfect. Got it on the first time. On to the next question. We are given that 1 hour before a football game, a sponsor gave away 5,000 special wristbands to the 10,000 people there at that time. If that's the number of people who arrived after the giveaway, then the function P equals F of S represents the ratio of people with the special wristbands to the total people in the crowd. So first, we're asked to find F of 2,000 and explain what it means in terms of the people with special wristbands. So I'm going to go ahead and evaluate that. F 2,000 equal to 5,000 over 10,000 plus 2,000, which is going to give us 5 over 12, or about 0.4167, which means that 41.67% of attendees had special wristbands once 2,000 people had arrived after the giveaway. Now we're asked to find F inverse of P. So to do that, we're just going to say, okay, well, P is equal to 5,000 over 10,000 plus S. We want to solve to get S on its own. So my first thing is I'm going to multiply this whole thing by 10,000 plus S on both sides. That's going to cancel out here. Then I'm going to go ahead and distribute that to get 10,000 P plus PS is equal to 5,000. Go ahead and subtract that, this value, to get PS is equal to 5,000 minus 10,000 P, which gives that S is equal to 5,000 minus 10,000 P over P. And then finally, for part 3, we're asked to evaluate F inverse of 0.35, which is going to look like inverse of 0.35 going to be 5,000 minus 10,000 times 0.35 over 0.35. And now that is going to give us a value of 42,086, or 4,286, which means that once 4,286 more people arrived, 35% had wristbands. Perfect. Okay, moving on to section 2.3, we're looking at transformations. So we're to suppose some function f is related to a function g by this relationship that we're given, and we are expected to list the transformations relating f to g, and then just list our choices, or just put them in order. So something I'm going to say to keep in mind is that we have to apply stretching before we can apply shifting. So what I'm going to focus on first is that we have this horizontal shift or horizontal compression first. So because this number is greater than 1, we know it's being compressed, and by a factor of 1 over that. So I'm going to say this is our first change here. Then moving on, because we're in X, we want to stay in X. We see that we shifted to the right by 5 units. And that's just because we're subtracting from the X. We know that X lies, so it'll go over by 5. Next, we have a vertical stretch now, because this is greater than 1, and it's kind of acting on the Y. We know that we're going to get a vertical stretch by a factor of 3. So that's going to be our third choice. And then we're shifting down 2. So then we are just going to end up with this order right here. Perfect. Moving on to section 3.1, which is linear functions. We're given that a bathtub was partially filled with hot water when the cold water tap was opened. 2 minutes later, the bathtub held a total of 48 gallons. 5 minutes after turning on the cold water, the bathtub held 61.5 gallons of water. Then we want to determine the rate of change in the number of gallons from 2 minutes to 5 minutes, including units. So what I'm going to do is just take the change in the number of gallons, 61.5 minus 48, over how much time had passed. So that's 5 minus 2 minutes. So that will give us a rate of 4.5, and that's going to be in units of gallons per minute, which can also be written as GPM. And then on part B, we're asked how many gallons of water were in the tub at the time the cold water was turned on. So what I'm going to do is I'm going to take that we were at 2 minutes. We had 48 gallons. And we know that the rate or the slope is going to be 4.5 gallon per minute. So if we kind of take this back to 0 minutes, we'd be doing a change of 2 times the slope. So if we said 48 minus 2 on 4.5, that will give us 39 gallons. Perfect. And then finally for part C, we're asked to write a linear function for the number n of gallons of water at time t in minutes after turning on the cold water. So we're given n and t are our variables. So n is going to be our dependent variable as a function of t. Now we're thinking of mx plus b form. Here, x will be t. We know that our slope, our change, rate of change, was 4.5. So I'm going to include that here. And we started at 39. So that is where we're going to get our linear function from. Skipping ahead to question 35, we're asked to use inverse trig functions to give solutions to our equation in terms of some integer k, with initial solutions between negative pi and positive pi. So just between these two angles. And then we're asked to show our work using any reference, or including any reference angles or other things that we're using to find our solution. So I'm going to start here. I'm going to get all of my cosines on one side and all of my other digits on the other. So what I'm going to do is I'm going to add 1 to both sides. I'm going to subtract 8 cosine x from both sides. That's going to give me negative 4.5 cosine of x is equal to 3, or cosine of x is equal to negative 3 over 4.5, right? So now what we're going to do is go ahead and evaluate that. And that is going to give us a value of 2.30 radians. Moving on to our unit circle, that is going to fall somewhere over here. And now we want to find another possible angle that has the same exact cosine, the same exact x value. So what we're going to do is we're going to carry that down to here. And what we're going to notice is that this is the same as negative 2.3 radians, right? So those are our two initial solutions that we're given, is negative 2.3 radians and positive 2.30 radians. So now our answer is going to be 2.30 plus 2 pi k and negative 2.30 plus 2 pi k. And remember, that's just because if I go 2 pi or some multiple of 2 pi radians around, I end up at the exact same spot. Moving on to the next one, we're given this function. What I'm going to do is I'm going to say I'm going to move it all to the left-hand side. say 2 cosine squared of x minus cosine of x minus 1 is equal to 0. And what I'm going to do from here is go ahead and factor that out a little bit. I'm going to get 2 cosine of x plus 1 times cosine of x minus 1 is equal to 0, which means that 2 cosine of x plus 1 should be 0, or cosine of x minus 1 is equal to 0. This gives us cosine is equal to -1/2, or cosine of x is equal to +1. Now, +1, that's going to happen exactly here at this point of 0 radians. There's not really another point that we can kind of carry that to that would have the same value. And then cosine is -1/2. It's going to occur here and here. And now these values are, this is 2 pi over 3 radians, and this way is 4 pi over 3. But in order to get this angle, you can go ahead and say 4 pi over 3 minus 2 pi, and that will be the same as -2 pi over 3, which is the same as just reflecting this angle across the x-axis. So now our solutions are going to be 0 plus 2 pi k, -2 pi over 3 plus 2 pi k, and 2 pi over 3 plus 2 pi k. These are our list of solutions. And then in the interval is going to be 0, 2 pi over 3, and -2 pi over 3. So now on number 37, we're using inverse trig functions to solve the equation in terms of k with initial solutions in this interval. So now what we're going to go ahead and do is just say, we're just going to take the arctangent. So arc tangent of theta is equal to arc tangent of -4.5. This is just going to leave us with theta. And then going ahead and evaluating the right-hand side, that is going to yield a value of -1.35. And that's where we're going to leave it for now. So this is the in the interval solution. And now if we think about it, if we have our unit circle here, we'll go ahead and just sketch something. Theta is going to be around here. This value is going to be the same at any coterminal angle here, but also anything across from it. So if we go pi, or if we go 2 pi back, we'll end up with the same value of tangent. So our list of solutions is going to be -1.35 plus k times pi, just because any number of times that we kind of go pi, like go to the opposite side of the circle or back, it's going to have the same value of tangent. Moving on to section 10.1, rate of change, question 38. We're saying that the function p equals p of t represents the population of a small town in Oklahoma at time t measured in years. So we're looking for the practical terms and meaning of dp dt. That is just going to be, obviously this is a derivative that we're looking at. So that means that this is going to be rate of change. Of population over time. And then for b, we're looking at, so if dp dt was a negative number, what's happening to the population? Now think about if our rate of change is negative, that means that our population was decreasing. Now flipping it to if our rate of change is a positive number, that means that our population is increasing. And now lastly, if our rate of change is 0, that means that we're not changing at all. So that, I guess, that's all you have to say. The population did not change. And finally, on to question 39. We are given that the graph of a function y equals f of x is given, so we are asked to mark segments of tangent lines on the graph in part A, and then in B, we're looking at regions where the rate of change dy dx is positive, negative, and also 0. Okay, so we are going to go ahead and say, I'm just going to draw some points here. So here at the very top of our function, we know that our rate of change is going to be about 0. Down here, our tangent line is going to kind of look like this. Go a little bit further, our tangent line is going to kind of look like that. And then just kind of on and on and on down either side. Just going to have the same exact slope at that point, which I'm not sketching very well, but that's the gist of what it's asking us to do, is just draw little segments of tangent lines along the curve that kind of represent what the rate of change is doing. So now, moving on, for part B, we're asked when is the rate of change positive? So that basically just means when is our function increasing? And that is happening from negative infinity up to this point here at negative 1. Now conversely, our function is decreasing anywhere past negative 1. We can see that that is our local maximum, so anywhere that we go past this, it's going negative. And it's decreasing all the way as x goes to infinity. And now finally, when is dy dx 0? That's going to be at here, our local maximum, at x equals negative 1. And now finally, for part C, we're asked to use information from A and B to determine which of the graphs could be the rate of change or dy dx. So what I'm going to go ahead and do is I'm going to just look at both of these, or I'm going to look at this one first, just one is at 0, so we can kind of eliminate some of our due process of elimination to figure out which graphs are not going to be the rate of change. So here at A, we know that it's 0 at negative 1, so that's correct. That's correct, and that one's correct. For D here at negative 1, it's not 0, so we know that that cannot be it. And then the same for E. They're both constant. Think about if I have a constant rate of change, that should yield a function that's a line up here. So these ones we know are not going to be, they're not going to be your solution. Moving on, we know that dy dx should be negative from negative 1 up to infinity. So if we look to the right of here, this one is going positive, so it cannot be A, because our rate of change should be positive. It's positive here, where it should be down here. On to B, this suffers from the same issue. It's positive, where it should be negative, so we know B cannot be it. That just leaves C, but just to be safe, we want to look at, if I go to the right here, it is indeed negative, so we're good. We know that C is the rate of change. And we're perfect. Awesome. Stay tuned for parts for the next few parts. We'll get those out soon. Yeah, thank you so much for watching.